Hello, everyone. I will start. Thank you, Thomas and Amir, for this very nice conference. And I know it's the last presentation. You're probably very tired, so I will make sure to be as simple as possible to avoid a lot of math and equations. So maybe you can get the best of the presentation. Okay, so this is the outline, quick introduction and motivation of our work, and why we are trying to use radars to monitor vital signs. And I will present to you a few works that we did during my PhD, and later some conclusions. Okay, so what are vital signs? So vital signs are biological indicators of life-sustaining functions, and they provide an objective measurement of how the patient is behaving. So they are the first step for any clinical evaluation. And why do we need to monitor them? So they provide a clear indication on how we should proceed with medical treatment. And more importantly, they provide early indication of patient deterioration. They are also used in the form of these charts as a tool for decision making in emergency units. So in which you provide a lot of vital signs, and then you can calculate a score that indicates how often you should come back to your patient, or if the patient is deteriorating faster or not. There are four primary vital signs, and during this talk, I will focus on the breathing rate and the heart rate. So the breathing rate, we are interested in the frequency and also in the shape of breathing, and common values for the breathing rate goes from 10 to 25 BPM for adults, and a bit higher for infants. The gold standard is still observation, manual observation, and but there are also other methods to measure, like epidermal spinomography and PPG sensors. For the heart rate, we are also interested in the frequency, of course, the pattern, and also in the variability. And here we have common values. And the gold standard is ECG, but also we have another types of measuring, another forms of measuring the heart rate. And what can be inferred? So, of course, from the cardiovascular behavior, we can infer a lot of things about the patient. And what is it's the most important predictor of cardiac arrest. And we can also prevent renal failure and meningitis. Okay, what is the issue? Outside critical care, the monitoring of vital signs is still performed through manual observation. And vital sign records are often inaccurate, incomplete, and even falsified. Just one number for you. In developed countries, there are estimates that around 83% of all vital signs documentation are incomplete. And regarding these charts that I showed before, the intermittent nature of monitoring, of collecting data from them, prevents a full exploitation of the vital sign information, and also limits response from the medical teams. That's why continuous monitoring is essential. And nowadays, it is still limited to intensive care units, and mostly based on cables and adhesives type of sensors. So this requires precise placement of the sensors in the chest and imply immobility restrictions. And also we have this, which was called MARSI, so medical adhesive related skin injury. And this is a very important complication, especially for premature newborns, also for burnet patients. Just one more number. There are estimates that around 50% of the entire the body surface of a small baby can be damaged each day just because of this kind of adhesives. So they put in one place, they do some damage, they put in another place, and they go doing damage and more damage. So that's why we are looking for contactless devices. We want to get rid of those sensors. And they have no confinement, no discomfort, no skin damage. And they are especially important for the long-term monitoring. We are moving now in medicine from a reactive approach to a more proactive approach, and where the medicine is going closer to the patient. So, and this takes us closer in terms of going into the patient house. So we are interested in long-term monitoring and going closer to our patients. Okay, and why using radars? So there are clear advantages of using radars for monitoring vital signs. They are skin light independent. They can penetrate blankets, for instance, and low power. They can be low power, low cost. Privacy preserving is very important. How they work? So, of course, now you are almost radar experts, given the nice talks that we had today. But the radar simply transmits some kind of waveform and gets the reflections which are coming back. And those reflections are modulated in a way by the chest movements. So the radar is seeing basically the chest movements. And we can look into this, the phase of our receiving signal to try to extract the chest movements. And from that, we can calculate the frequencies that we are interested. Most research is around 24 gigahertz, but due to the automotive industry, we are migrating to 60 and 79. Oops. Just a few experiments, and here we can see how precise the radar can be. This is a speaker device, so we can set up to be so that the membrane is moving back and forth like the chest. And here we were comparing the movement that we see from the radar and with the movement that we see from a laser device. So this was the laser device here. And this is not Vivian that you met there in the demo, but this is Ophelia, our other baby. And we were also measuring how she is breathing. And here you can also see how precise the radar can be. But of course, we are in very specific and perfect conditions in an anechoic chamber, so everything is easier. And regarding signal processing, so this is just the basic signal processing block diagram for monitoring vital signs. And we have a pre-processing step, which is just related to classical radar signal processing techniques. So we are trying to detect the target and locate the target. And as soon as we do that, we can extract. So there are common classical signal processing techniques for the pre-processing step. I will not focusing on this. But as soon as we detect the target, we can go to the phase demodulation stage, in which we, from the complex samples, we are trying to extract the phase, which is related to the movement of the chest. And later we take this displacement, what we call displacement, and we try to process a bit to increase the signal to noise ratio and also the signal to interference ratio. This is the filtering part. And last one, we take the signal, we will go for the estimation to really calculate the frequencies. So we use this block diagram to guide us through the next sections of the presentation. So now let us focus on the phase demodulation part. So we have complex samples and we want to recover the chest movement. So this is a recent published work about unlimited sampling. So for vital sign monitoring. And what is the motivation here? The state of art is using what is called arctangent modulation. So we just try to extract the phase by applying an arctangent operation. However, this requires unwrap operation before, and the unwrap operation, due to the bounded image, has when displacements are larger, you have these wraps, and you need to unfold this information. The classic unwrap it has very basic assumptions. So whenever your phase jumps are bigger than pi, you just add minus or plus pi and 2 pi, and then you can correct that. However, it fails under quick phase variations. And these quick phase variations can come from random body movements. So whatever is moving closer to our chest, or even larger chest displacements. There is this theoretical condition, which is ITOS condition, so defining theoretical bounds for the performance of unwrap. And we can see that the first order difference should be smaller than the wavelength. Okay, this is just one example of unwrap error. And you can see a chest displacement here. And at some point, we have a random body movement. And this is causing the unwrap in red to fail. And what is interesting here is that here in the spectrum, in the blue case, which is the true displacement, even with the interference, the random body movement, we can clearly still see the correct peak, and we will be able to measure correctly the frequency. However, if we do wrong demodulation, we will inject nonlinear errors, and that will be very tricky to be able to estimate here after that. So here we are leveraging the powerful framework proposed by Professor Bandari. And the idea is to use the limited sampling to replace the unwrap operation. And this theorem was already shown here before. I will not go into the details, and not also in the algo. But the idea is that if we have a band limited signal, and we can take the modulus samples of this signal, and we will be able to recover this independent of the wavelength or independent of the amplitude of the interference here in our case, as long as we respect some sampling frequency. So just a few simulation results here. We simulated different kinds of body motions. And here we have the recover error, so the normalized recover error. And when we are using the conventional wrap here on top, we can clearly see the linear relation that I showed in the previous slide. However, when we use the limited sample framework, as soon as we reach a specific sampling frequency, there is no more any dependence with the amplitude of the random body motion in this axis here. So just to conclude this part, so these are just different results, consider different operating frequencies, and we see here, so below is where it is not working properly, and for that side is where it is working properly. We get a low error, so for a limited sampling, we get most of the time a very good recover of our signal. And for conventional unwrap, this bottom lines here, we just see the linear relation showing that most of the time we cannot really recover our signals. And this dark line here is related to the theory of unlimited sampling, which says that there is a sufficient condition for recovery, but this is not required. And we can see that we can recover with much lower sampling frequency. Okay. So now let us assume that we managed to extract the chest movement correctly. And what we want to do now, we want to remove whatever interference we have, or we want to improve our signal before going to the estimation part. So luckily, our work was not only theoretical. So this was our work in the hospital with the babies. It was published on Nature last year. So we were trying to monitor 12 premature babies in the incubators. So we collected 3 measurements of 25 minutes for each baby in the supine and prone positions. So supine when the chest is facing the radar, and prone when the back is facing the radar. We also collect data from twins in the same bed. So we were trying to see how an additional baby could influence our measurements to the main baby that we were trying to see it. We were using CW radar 24 gigahertz. And the idea of this work was to provide seamless operation in the intensive care unit. That means that there was no interference from ourselves into the measurements. So the babies were moving freely, they were crying, they were yawning, they were, do everything baby does. There was also visiting from the parents around. So we have a whole set of different interference coming around. So the biggest issue here, the challenge was to remove this kind of interference. And I guess it was the first time that we showed results with all this kind of interference. Mostly every time people are just showing results when you have minimal movements. Okay, and what we propose to remove this interferences. So we are assuming here, it's our we are assuming that the random body movements, that our kind of interference is sparse. So that means that considering the size of our processing window, they are small in relation to this size, and they are not happening often. And this is in contrast with the constant nature of briefing. And this is specific time frequency features. We can see it in the spectrogram. So this is just one example of a nice briefing signal in which we have two segments of interference of random body movement. And we can see this in the spectrogram. So here we propose to use the NMF, so the non-negative matrix factorization. So we'll not go too much into the math here, but the idea is to use a factorization technique to break our spectrogram into two kind of matrices, W and H, in which W contains our frequency components and H contains our timing components. And then, so there is a optimization problem. We can use a simple gradient descent to solve this. And after this is done, we can look into the time basis and we can look for our sparse components, strong and sparse components. And then we can apply some kind of detector to remove this basis from our signal and rebuild our spectrogram only containing our desired information. Just to make an analogy, if our input signal was a song, a music, the W matrices that we get from the NMF are similar to chords that we are playing. So A, B, C, D. And the H matrix corresponds to the time activation of these chords. So it's like the moments we are playing and how they fade over time. And then we can rebuild our spectrogram just using the layers that we want. So this is just one of the results. We have the original signal with random body movements, original spectrogram, and those are the W and H matrices. And when we look to the time activation matrices, we can see these strong guys, which are sparse. They are only strong in this part. Most of the time, they are close to zero. We can rebuild our spectrogram, and then we can have our clean signal here. Just a summary of the results. So we managed to get almost 20% of improvement. That means 4 BPM, close to 4 BPM, and our accuracy was close to 80%, 6 BPM accuracy, close to 80% all the time. Overall, our MSE is smaller than 7 BPM. Just to be able to compare to other works, so during minimal movements, of course, the performance was much better, and we got more than 80% in all scenarios. Interestingly, we got best results in prone position. So when the back of the babies was facing the radar. And there is a nice explanation about it. This is not from me. This is coming from the doctors that were working with us. This is because the ossification of the ribs begins at the back. So because these babies are very premature, they don't have the ribs fully formed yet. And because the ossification of the ribs begins at the back, they may have a more homogeneous breathing pattern from the back rather than from the chest, which doesn't have bones yet. Okay, and finally, so we can assume now that our signal was properly filtered. So we have a nice signal. Let's go for the frequency estimation part. So this is the last work I will show you today. Was published recently. It's about adaptive nonlinear square estimation. And we proposed a few things in this work, but I will focus only on the estimation part. And what is the idea here of this NLS approach? We were looking for different models for representing the chest displacement. What we saw in many of them was reference to the presence of harmonics. And so we decided to use the NLS nonlinear square approach because it takes advantage of this harmonic structure. Yeah, so the idea is just we can represent our chest displacement as a summation of harmonic related components, and we can rewrite this into matrix notation. We can define our NLS problem, we can calculate our NLS estimates, but what is really important here is that all this fancy math boils down into a very efficient implementation using fast Fourier transform and a simple grid search over the frequency candidates. This was really important to us. However, here comes one more challenge. So now we were trying to estimate the heart rate, and what happens is that the spectral region of the heart rate of the heart rate, the heart frequency, is usually overwhelmed by breathing harmonics. So if we breathe around 20 BPM, and our heart rate is close, I don't know, 60, 70 BPM. So the second, the third, and the fourth harmonics of the breathing will go over the heartbeat region. So it is very difficult to estimate the heartbeat from the region of the fundamental frequency. However, higher order harmonics of the heartbeat are only influenced by noise. So our idea was, so let's try to estimate not only using the fundamental frequency region, but also using the higher order harmonics of the heartbeat. And so this is the basic idea, generate multiple estimates. And how do we decide which estimates are good? There is no way to know if we will have enough energy in the heart signal to see the second or the third harmonic. So as we don't know that, the idea was to always calculate these estimates, and then we could give all those estimates to a Kalman filter. And the Kalman filter can use the gating process to decide, so it is doing its own estimation all the time. It can use the estimation process to decide which new estimate are good or not, which is the best one. So we can split our NLS spectral region into different search regions, and we can calculate 3 estimates for the heart rate, and we give everything to the Kalman filter and let the Kalman decide. So some experimental results. So here we're using 79 gigahertz TI radar device with 1 transmission, 4 receiving channels. So just common signal processing steps here from the pre-processing part, beamforming, range Doppler map, extraction of our chest displacement signal, and here we have breathing and heartbeat signals separated. The subjects were using a shirt called exoskin, which contains ECG sensors and breathing sensors as we were using for ground truth. And regarding scenarios, so here we were emulating 3 types of scenarios, actually 4 types, common to the office environment. So we were emulating as we were texting using a phone, as we were typing using an external keyboard, and as we were mousing, controlling a mouse device, just to see how these small continuous movements, which are closer to the chest, how can they will affect our estimation. This is just one example when the subject was typing. You can see that most of the time you get a good displacement signal. However, in some points, because of the small movements, you get some errors in the demodulation, and then the estimation becomes really difficult. This is just one estimation set, and you can see that if you use conventional techniques like just a simple DFT estimation, most of the time you cannot really get nice values, but using our proposed technique, we were very close to the true values all the time. Just a summary of all results here. We are what we call accuracy is the amount of time that our estimation is close enough to the true values, and clinically accepted values for the accuracy are around 2 BPM for breathing and 5 BPM for heartbeat. And this is what we get. It was much better than the clinically accepted values. RMSE values were very low for the heart rate, also for the breathing. And yeah, what is interesting here is that if we look into, if you remember our 3 search regions, we were looking for the heart rate harmonics, we can see that around 35% of the time, we could not get good estimations from the fundamental frequency of the heartbeat. So that proves that looking into the heart rate values in the higher harmonics are really helping us in get a good estimates, especially when we have the harmonic influence of breathing. Okay, just some takeaway messages. So radar vital sign monitoring is based on the phase analysis of the chest wall movements. And estimation performance is strongly affected by breathing harmonics and also by random body movements. Big challenges is dealing with multiple targets when they are moving freely and also speaking. And yeah, maybe next directions we can use multimodal, multi-sensor approaches and learning techniques. How do I still have time? Yeah. So this is just one video that we recorded with a real measurement and okay. Maybe we can just move a bit to the 2 minutes. So here we're using the same ground truth device. The radar is in front of me, and you can see the chest displacement. So I was not, in the beginning, I was not doing any additional. So we have a very good chest displacement, a very good estimation. However, now I'm speaking random things, so we can see how speaking affects our estimation. And the thing is that when we speak, our breathing pattern becomes speech dependent. So we only breathe when we stop speaking. And then we get these crazy things over there. And of course, estimation goes wild. And at some point I will stop speaking and I will go into apnea. So I will stop breathing. So we can see how this affects. Just wait a bit, and this is happening soon. Okay, so now I'm not breathing anymore. And then you can see that the chest displacement is over. And this small variation that we see here is the chest displacement only to the heartbeat. So this is how the radar can see it. And then we can see, of course, breathing values going down. And also what happens with the heartbeat when we are not breathing. So this is the shape of my heartbeat. And then at some point I will come back breathing again. And we can see now clearly the displacement. And it is interesting now that we will get some strange things in the breathing pattern. Some strange shapes appearing, and I believe this is because my heartbeat was beating stronger to recover, and we can see this strange stuff. Anyway, just to show you a bit of how challenged this can be, and you can see that this is even a very simple scenario where we are not breathing too much. Okay. Can we? The baby data set is available on our website, RadarMam. So if you have interest, you can download the data from the babies and you can try something nice. You can discuss anytime. And yeah, thank you for your attention.
Oh, thank you. Questions?
Thank you for your wonderful talk. Just a naive question, perhaps. Does the level of hydration affect the radar measurements? Hydration, like the amount of water in the body?
Yeah. I believe it should affect effectivity, and then we can get maybe better signal if we have more water. But yeah, never thought about that. But I believe it would affect for sure.
Okay, thanks.
Other questions? I'm sure you have one.
So I have a small question. So here up to now, when it comes to estimating either the heart rate or the breathing rate, it's still pretty much frequency based and like Fourier based in a way. But as you clearly mentioned, depending on what you're doing, so if you're like talking, breathing, apnea, the different shape varies. And so you got in a problem where depending on what you do, you have different type of models. And so in a way, do you think that it would be interesting to move away to some extent from this type of Fourier analysis and more either dictionary or even deep learning, where you feed the data and in a way you get both the classification and also the information that you're looking for, especially when you look also at random body movement, where it's also a really complicated problem because they can exist in a way in the same frequency range.
Yeah, I totally agree. Maybe learning approach can be a very nice solution. The only issue I can see is how to get enough data to be able to work nice with this. And I don't believe that one single type of approach of estimator will be enough for providing nice vital sign monitoring in more real situations. Maybe we may have a combination of approaches, and then we can get, I'm also suggesting a combination of sensor devices, so we can have something more robust, because people are doing this for a long time, and we still don't see many solutions in the market. So the challenge is important, I believe.
Okay, I just have another question. So you're mentioning here multimodal, but in a way, sometimes people say that this type of wireless vital sign monitoring is really good because it also guarantees privacy.
Yeah.
But what would you see as another sensor that would increase the quality of the estimation while guaranteeing the privacy?
Yeah, this is tricky because most everything people is doing is based on radar cameras. And if we come back to cameras, we don't have privacy anymore. We have good quality, good features we can get from cameras, but no privacy. So this is a tricky question. I don't really know which other sensors we could use it.
I don't know as well.
Thank you for the nice talk. Like, it's not really a question. Like, I just want to know what's your opinion on it. Like, for example, in the lie detector, people, they used to monitor the heartbeat of somebody who's giving the speech and try to detect whether that it's truth or lie. Because when people lie, their heartbeat goes and the breathing pattern also changes. So, and since yours is contactless, it could be used in an invisible way, so that they don't know they are whether monitored. So have you thought about this, and just your comments on this? Thank you.
If I remember correctly, the first application of vital sign monitor was a lie detector. So that came from the military. That's a long time ago. So yeah, but then it comes to the challenge of how to measure correctly when the guy is speaking. That's what I try to show here. But anyway, this is a very nice problem, and I believe it could be used, yes, for sure. Also for security reasons. So if you put some kind of devices in airports, and you can try to see what is happening with the heart of the guy, which is maybe carrying some drugs into the X-ray. So maybe you can infer something from that.
I just had one more question with application to monitoring vital signs of babies. How cost effective could this be? Let's say, do you envision deploying such a system, let's say, to Africa where babies are malnourished? And would this be an affordable system that could be deployed in mass? Thanks.
Yeah, I believe that because of the automotive industry, the prices of chipsets are really going down now. So this is becoming really a consumer application. So that is a good indication that may be possible to deliver these in underdeveloped countries. And the thing is how to do it, because right now the setup we are putting the radars over the warming bed, yeah, so maybe this needs to have a bit more thinking regarding the product engineering, how we can make it viable and cheap. But yeah, that should be done.
I have another question. Sometimes, or actually very often, when I work with radars, I run into people are worried about electromagnetic radiation when you introduce, especially when you introduce something new. Is this something you have encountered? I mean, information, I guess you need to have a lot, but do you have that problem?
Yeah, technically, these devices are very, very low power, so there is no risk. The power is less than a mobile phone. However, no one knows that. So it was very, very difficult, and it still is very, very difficult to get the parents to accept that we are monitoring their babies, especially because they are in a moment of emotionally weaknesses. So we have a few guys in the hospital just doing that. So trying to convince parents to let us to try to monitor the babies, and it is really difficult. even knowing technically, we know technically that is not a problem, but when you say radiation to any parent, okay, no, he doesn't want to discuss anymore.
Okay, thank you.
Thank you.
Oh, was it?
Minimum risk, right?
Yeah.
Because nobody has done study on 77 gigahertz radar, especially for babies' bodies. Like there are some FCC studies in the US on exposure for how long, how much power you can expose the human body to for specific frequencies of RF or electromagnetics. But 77 gigahertz, I don't know if anybody has done those studies. So they're at lower end, and especially for babies whose bodies are smaller. We may not be at risk, but
Yeah.
for them, there needs to be some more detailed study. The other question I had for you was, you said you originally were at 24 gigahertz where most of the vital signs monitoring systems were early. Is there any difference in performance between your algorithms when you go to 77 versus 24? Because now you're able to pick up
Yes.
much smaller movements at 77, right?
Yes, the rule of thumb is that when you increase the frequency, you increase the sensitivity to the phase. So things should get better at higher frequencies. However, there are other issues which comes with higher frequencies. One example is just the unwrap thing. So you have more wraps on your face, so it's more difficult to correct everything. I believe everyone is moving to 60 and 79 because of the automotive industry, not because it is better or worse. So just because it's becoming cheaper and easier to use. Yeah, but technically, I think it should be a bit easier going higher, and we have a less penetration, but still enough, I believe.
Okay, any more questions? If not, let's thank Gabriel and the other 4 speakers.